Okay, so this is the next in our series of derivations of the electric field from different shapes of continuous shapes. This particular shape that we're going to be doing is a ring of charge. So when I say a ring of charge, let's say you have a ring that looks like a hula hoop or this ring, right? It's a ring. And you charge it up. And I don't know, say you give it a bunch of positive charges. How it got positive, I don't know. But let's ask a couple questions first. Let's say you're right at the center of the ring. What direction does the electric field point? There's no electric field in the center of the ring. How come?
So the charge is on the outside.
Yeah, because if there's a charge here making a field down, there's a charge in the bottom making a field up, and the two are going to cancel. Okay, so fine. The field is 0 inside the ring. How strong is the field at infinitely far away? 0. So if the field is 0 in the middle, and the field is 0 infinitely far away, does that mean that the rings don't create any field?
No.
Wait, let's graph this. Let's make a graph of this. Here's what I'm talking about. Let's say, let's see. Let's pick a color. All right, here's a set of axes. We know the field is 0 at the center, and we know the field is 0 at infinity. Does that mean it's 0 the whole time? No. What do you think it does? It asymptotically approaches 0 from 0?
No.
Oh. Oh, so it's 0, then it goes to infinity.
No. Goes to a value.
What's it do? It goes to some value, and then what?
Drops down.
Drops down again. So maybe it goes like this. Woo!
Yeah.
That's supposed to be an asymptote, sorry.
Less silly.
Can I backtrack that? Apparently not.
Oh, Jesus.
Whatever. Anyway, so we think that the field in the middle is 0, and then in infinity is 0, and then when you're not at infinity, it must build up and then decay away again. Isn't that cool? That's it. Okay, well, let's see if we can figure that out. So what we want is an equation that's 0 at 0, is 0 at infinity, and not 0 in between. It got some hump, some maximum peak value, and then decays away again.
Wow.
Sound good? All right, so let's create a function. So we got to do that by integrating, right?
Yes.
All right, so when you're setting up an integral, a couple things keep in mind always. First task is we need to decide what direction we're going to integrate over.
What?
Like, where are all the charges?
On the circle.
They're on the circle. So here's your circle. Here's the x-axis. Here's the y-axis. So the circle's in the xy plane. What do we call the axis that comes out the middle of the circle? Z. So the circle's in the xy axis. So should we integrate over x?
No.
No. Should we integrate over y?
No.
Should we integrate over z?
Yes.
No.
Why? I was kidding.
No. What should we integrate over?
Both of them.
X,
All
Y,
three
X.
of them are.
How about angle?
No.
Oh.
This is
What?
No.
No.
I was thinking parametric.
Right?
No.
We're gonna integrate the angle around the circle.
Why?
Why? Because that's the easiest way to do this.
No.
If you want to integrate over x or y, guess what you got to deal with?
Wait, why?
A horrible equation.
Let's do it. It's literally
Yes.
cosine.
I know. It is literally way more complicated than integrating around the circle.
That's what you're saying that this is easy.
So.
Yes, this is easy.
It's easier than integrating.
Yes, you know what the integral ends up being?
One.
2 pi. Right?
Wouldn't that be parabola? Like, okay, I'm just gonna go along with it.
Right. We're going to integrate around this circle. Stop the convulsions. You'll be okay. We want it because if you think about it, where are all the charges? Around the circle. So we're going to take this charge, then we're going to take this charge, then this charge, and 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 then this charge, all the way around the circle. What do you notice about the distances from all the charge from the center of the circle?
They're all the same.
They are all at a radius of r. Got it?
Yes.
Now, if they're all at a radius of r, guess what?
It's a circle.
What is,
It's a circle.
Yes, it is a circle. It is a circle. I gotta poke at my iPad here for a second. All right, so let's look at the iPad. This is a circle, right? It's got a radius of r, and each little piece of dq, well, each little piece of dq has a length of dl, right?
Yeah.
Or ds maybe. But every piece of dl or ds is going to be the radius times the angle, right? If you're measuring in radians. But here's the really cool part about doing it this way. You guys ready? Isn't every single particle of charge at a radius of r from the center?
Yes.
And so isn't every single particle at a constant distance from point P? Like from here to here to P, from here to P, from here to P, that's all the same distance, right?
Yes.
Diagonal?
Ri is going to end up being a constant.
So Ri is a constant, yes. And well, what do you notice about dq? Ri, yeah, the distance from here to here is the same as the distance from here to there, right?
What happens if you move on the z and the y-axis?
On the z and the y-axis.
So say point P was to move up the y-axis, but remaining in the same spot on the z-axis.
That is a different problem
Oh,
that you will not be asked because this is not a multivariable calculus class.
okay.
Come on,
I don't know. It was
No, it's a perfectly valid question. The first time I did this problem, they asked me this question first, and then they said, well, what if you pick a point that's up here somewhere as your point? And I was like, and my head exploded. Then I realized I had to do multivariable, and it was a horrible problem. This is not a horrible problem. This is one of the easiest problems.
We're just finding the electric field along the z-axis.
Yes.
so.
Yes, it is boring. And that's all that you're going to be required to do. So deal with it.
Oh. Sorry.
Yes.
Do we need to care about like the width of the ring?
Oh, is that important?
So wouldn't that mean like if it was like within that width there'd be no field? Just inside the
Oh, you're saying off center, like somewhere along the y-axis?
along the z-axis. You know like the
Well,
You
the
would extrude the circle farther along the z-axis.
oh, if this were not a simple ring, but it were rather a tube,
yeah.
we are not going to do that problem yet.
We are gonna do it though.
You can if you want. All right, we are not going to do that problem.
So, is the graph like this with like a hole at the center?
I don't know what the graph looks like. We're going to have to figure that out. We guess that the graph, it's going to be 0 in the middle and 0 at infinity, just like we have drawn here. And then it's going to go up to some not 0 value and then come back down again. All right. So, anyway, let's continue. Because we just confused half the class for no particular purpose. All right. So, back to the question at hand. Let's say we want to find the on-axis field. And when I say on-axis, I mean along the z-axis. The field at a point P that's along the z-axis. Here's the trick to this problem. Every single bit of charge is at the same distance from P. Wouldn't you agree?
Yes.
Means you don't actually have to integrate anything.
Okay.
You can just use the whole charge because all of the charge is at a distance of Ri. Even though all the charge is in the same physical location, It's all the same distance away from P. So you don't actually have to integrate at all for this problem. Here's what I mean. We're going to pretend like you did have to integrate for a second. We're going to say we're going to pick this point up here. We're going to call that our little piece of dq. It's at a distance of ri. It's at an angle of theta. And we know from symmetry that we're interested in just the z-axis component, right? So we're interested in dE cosine theta from yesterday. Remember that?
Yeah.
So dE cosine theta. And let's see, dE, that's kq over r squared, right? So it's k dq over ri squared times cosine theta. Good?
Yes.
Now, cosine theta from yesterday we know was, let's see, here's the triangle, here's theta, so we know it's adjacent over hypotenuse, so we know it's, I don't know, z, that's the distance along the z-axis, z over ri. But ri is square root of z squared plus r squared. So cosine theta is z over square root of z squared plus r squared. Good so far? All right. Now, also from yesterday, we know Ri is Pythagorean theorem. Ri is the radius squared plus z squared and square root that. So I know my answer, my electric field is k dq times 1 over r squared times cosine theta. Simplify all that. So k dq z over z squared plus r squared to the 3/2. And that looks really, really awful. However, it's not.
Because of everything in there's a constant.
Every single thing in there is a constant.
So it's just that times q.
That times q. Exactly. There is no integration required. It's the integral of a constant. Are you guys okay with this one?
Yeah.
All right, good, because it's easy. So the answer is k times zq over z squared plus r squared to the 3/2. That's the answer. You didn't have to integrate.
I thought it said something about you find the whole charge at that point, so why do we stick with DQ?
Well,
Isn't that essentially K?
0 to q. Yeah, when I first started the lecture, I mentioned we're going to integrate around the loop. Yes, you can integrate around the loop, or you can just not bother.
Isn't it just... Wait,
What's 1 over 4 pi epsilon naught?
Z.
Oh, z. Z is the distance
I thought
from...
it was a 2, so...
Yeah, sorry. zq over z squared plus r squared to the 3/2. Good? All right, so what's this equation actually look like if z is 0?
0.
It should be 0 because it's in the center of the field.
Yeah, it's 0. It's 0. So it's in the center of the ring, the value is 0. What's this equation look like if z is infinity?
Z squared...
0.
So it's a bigger
Interesting.
thing on
Is it top heavy or bottom heavy?
Bottom heavy.
It's bottom heavy, so it asymptotically approaches 0 when z is infinity. Okay, that's interesting. So, can you look at that equation and figure out when the field ought to be a maximum value? Like, at what distance away is there, how far away do you have to be from this ring in order for there to be a maximum field? And why does it reach a maximum and then fall off? Oh, no one. Wow.
Because it's
Less
touching
than
the
one.
plate and then it's going away.
I'd say...
There's my ring.
I would agree with her, somewhere less than
So
1.
you're gonna be like,
Why is the field 0 in the middle?
Because
it's
everything's
getting
canceled
pulled
out.
It's not that the field should be 0, it's just that all the fields cancel out in the middle.
field is 0.
The net field is 0. Why is the field 0 at infinity?
Because it's so
Because
far away.
it's
It doesn't
infinitely
matter.
far away.
Because the contributions to all the fields from all the points is 0 because it's too far away.
Sure.
So at what point should the field be a maximum?
Right next to it.
Right when it's touching.
Like right next to it or out a little ways? Like a 45-degree angle?
When it's
Yeah, isn't that an interesting question?
Shouldn't it be like a? I feel like it's gonna be like a at a distance
Where
equal
the
to the
top and
radius of
bottom
the
are
ring or
equal.
something with it, like that.
Yeah, so where, like, Well, think about it this way. You have two competing effects for the field, right? One is the 1 over r squared effect, which is this term right here. And one is the cosine theta effect. So you've got to pick a distance where 1 over r squared times cosine theta is maximum. Yeah.
I'm confused because on the thing it says, because wouldn't you be able to take the derivative of this function and find out where the 0, but the only
Sure, but that would be
zero.
boring.
Yeah.
We're trying to figure it out conceptually.
Oh. Okay.
Yeah, no, you can absolutely take the derivative of that function and then get your answer. And that would be the math plug and chug way to do it. But I'm trying to get you to think about what things are affecting it.
So that's easy.
If you got to the ring, it's just larger and get one because your z value would be getting smaller and smaller since it's on the bottom.
Yes, you would be, the individual field contributions would get bigger and bigger, but the angle starts affecting it. Because now the angle is like a really steep angle, right? And it has a very small, due to the angle, it has a very small z component. Most of the component is in the xy plane.
Wouldn't be on the z-axis, but like infinitely close to it.
Oh, so you're saying it asymptotes up like that and then has a value at 0?
Well, we know what this looks like. It's like a. No, it's
Do
not.
you?
I look
It actually, if you put it in your calculator, you're going to get a shape that looks like this.
That's weird.
Yeah. You're weird.
Wow. Okay.
So anyway. Oh, what about on the opposite direction? What's it do? When it hits 0, what happens on the other side?
It's symmetrical. It's
It-
symmetrical.
It goes like that.
Like a mirror.
Yeah, because, why's it got to do that? Because it's got to point the other direction. Field's got to point the other direction on the other side, right? Okay, so anyway, that's just something to think about. It's kind of a cool problem, but there's no actual integration involved. Yeah.
At 0, wouldn't there be a singularity? Even though we say the field's 0, but wouldn't it be 0 plus 0 to the 3/2 multiplied by 4 pi epsilon naught, which is 0? So 1 times.
Oh, are you looking at this equation right here?
Yeah.
Okay, so 0 divided by something that's not 0.
What would the bottom be 0?
The
No.
radius,
The radius isn't 0.
Oh, I'm sorry. Yeah.
Yeah, radius isn't 0.
This is a circle and
Yep.
this is
All right. So, yeah, now if the radius was 0, you'd have a point charge.
Yep.
All right. So anyway, let's keep going. E field of an arc. This is the setup for 2002 E1, which is in your packet. I'm not going to give you the answer to this. This is something you're going to have to do on your own today. But the setup goes like this. You have an arc of charge. It's an arc. It's a 120-degree arc. 60 degrees this way, 60 degrees that way. And instead of putting... Yeah. This is a two-dimensional problem, not a three-dimensional problem like the previous one. If I say center of curvature for an arc, do you know what I'm talking about? Like all arcs have a center of curvature if they're circular arcs. So that is at the center of that arc. I want to know the field. Which way does it point? At that point, which way does the field have to point? Assuming this is all positive. It's got to point directly to the right, right? Okay, so I'm interested in the field that points to the right at point P. And we know that, well, if you pick any random point, it's not going to point exactly to the right, so you got to do the cosine of the angle. So I'm interested in, once again, DE cosine of this little angle in here, which isn't 60 degrees. So d cosine theta, it's kdq over r squared times cosine theta. Now, I don't remember in this problem if they give you a linear charge density or not, but if I give you a linear charge density, what's that mean? Charge per length. Well, charge per length, I give it to you in this problem, which would be dq over ds, would be 1.5 times 10 to the negative fifth coulombs per meter. And also, because it's an arc, we know s equals r theta, or ds equals r d theta, which means dq, excuse me, dq is charge density times ds, and ds is r d theta. So dq would be charge density times r d theta. So there's a little bit of trickiness setting this up. So substitute lambda r d theta in for dq. So we got k lambda r d theta over r squared. But since r and r, one of those r's cancels, and you end up with k lambda over r cosine theta d theta. K is a constant, lambda is a constant, r is a constant. Theta is the only thing you actually have to integrate. So cosine theta. And you should get an answer. Does that make sense? So your variable, you're integrating over this angle, which is what I had mentioned in the previous problem, but you didn't actually have to do. Sound good? All right. So today, your job is to go to your packet and actually try these problems. Good luck.